Agentic era explains disruptive breakthroughs that shift our understanding of artificial intelligence. Researchers at Stanford University explore the transition from data fitting to physical discovery in their study From Kepler to Newton. This research investigates how three minimal architectural biases can guide transformers to learn true world models instead of just predicting tokens. By analyzing the Kepler-Newton phase transition, the study determines if a generic architecture can move from observing geometric orbits to calculating mechanistic forces. The findings suggest that specific structural constraints are necessary for neural networks to discover the underlying laws of physics. This work provides a concrete blueprint for building AI models that function as autonomous scientific discoverers. A fundamental inquiry in modern machine learning is whether general-purpose AI architectures can transcend their role as statistical predictors. While current models excel at forecasting next token sequences, it remains unclear if they can discover the objective physical laws governing the universe. The transition from fitting empirical curves to uncovering mechanistic rules represents a significant leap in artificial intelligence capability. This research addresses this by examining if standard transformer designs can be structured to reveal the hidden mechanics of motion. By testing these models against the foundational principles of physics, the study investigates the limits of neural network flexibility in scientific discovery. The ultimate goal is to determine if AI can move beyond mimicking observed data to identifying the causal invariance of physical systems. The researchers established two-dimensional planetary motion as the ultimate litmus test for model intelligence. This domain provides a clear benchmark for testing foundation models. It determines whether a model can reconstruct the principles of classical mechanics. The experimental setup utilizes a GPT-2 scale architecture. The model is trained on a massive dataset of 20 billion tokens. To handle this computational load, the researchers employed 8x8 The core argument is that models must recover established laws first. If they cannot, they will likely fail to discover entirely unknown laws. This simulation of elliptical paths measures the transition to mechanical understanding. This high-scale environment allows for a rigorous evaluation of architectural choices. It examines how these choices influence the emergence of a physical world model. Standard transformer architectures often suffer from a phenomenon described as the prediction illusion. These models can achieve high predictive accuracy by forecasting next token sequences effectively. However, their internal representations often fail to encode essential physical principles. Specifically, the models struggle to represent that gravitational force is proportional to the inverse square of distance. This discrepancy highlights that the model is merely predicting tokens based on statistical proximity. It is not actually calculating or understanding the underlying physics of the system. Without structural guidance, the transformer treats spatial data as arbitrary symbols rather than a continuous mechanical process. This lack of physical comprehension limits the model's ability to generalize beyond its training data. Consequently, high accuracy does not necessarily imply that a model has discovered the governing laws. This finding underscores the need for inductive biases that move beyond simple pattern recognition. To bridge the gap between statistical prediction and physical discovery, the researchers introduce three minimal inductive biases. These architectural constraints act as foundational pillars for building a mechanistic world model. The first bias is spatial smoothness, which aims to fix the model's internal coordinate map. This ensures that the model perceives coordinates as a continuous and fluid spatial field. The second bias is spatial stability, which focuses on mitigating the accumulation of numerical errors. This allows simulated systems to maintain long-term consistency without collapsing. The third bias is temporal locality, which forces the model to focus on the immediate past. By restricting the context, this bias encourages the discovery of the fundamental laws of motion. These three interventions are designed to transform the transformer into a system capable of physical reasoning. Together, they create a structured environment where causal invariance can naturally emerge within a general-purpose neural network. A major obstacle to physical comprehension is the discretization flaw inherent in default tokenization methods. Standard transformers process continuous spatial coordinates by binning them into discrete tokens. This process fundamentally shatters the model's spatial awareness. When coordinates are discretized, points that are physically close in space can be assigned to completely unrelated embeddings. The model effectively loses the ability to perceive continuity between adjacent regions. This loss is evident when contrasting smooth physical waves with a pixelated, fragmented representation. Because distance calculation is critical for laws like gravity, this fragmentation is catastrophic for scientific discovery. The model cannot compute force accurately if it perceives space as a collection of isolated blocks. This finding suggests that standard tokenization is ill-suited for tasks requiring fine-grained spatial reasoning. To learn physics, the architecture must find a way to preserve the smooth transition between coordinates. The experimental results confirm that baseline learned embeddings fail to maintain fine-grained spatial continuity. While the model captures coarse relationships with an R-squared value of approximately 0.86, it lacks precision. Visualizing these embeddings reveals a noisy point cloud instead of a smooth color wheel. Although some colors are organized into loose clusters, they lack the seamless transition found in true spatial continuity. This fragmentation indicates that the model cannot reliably identify nearby points in physical space. Without an accurate internal map, the model finds it impossible to compute exact distances. Because gravity depends directly on distance, this failure prevents the discovery of physical laws. The baseline architecture essentially sees a distorted and low-resolution version of the environment. This evidence proves that standard learning processes do not automatically result in a coherent physical world model. Specific interventions are required to fix this fragmented perception of reality. The emergence of a coherent spatial map is governed by specific scaling laws involving data, vocabulary, and model dimensions. The research quantifies this relationship through a power law formula. Here, 1 minus the R-squared value is approximately 0.52 times the data volume to the power of negative 1.15 times the vocabulary size to the power of 1.33. This indicates that a smaller vocabulary size actually forces the model to develop better spatial continuity. Larger volumes of training data also improve the quality of map emergence. However, performance plateaus rapidly once the dimension count reaches approximately 8. These graphs show that increasing the number of dimensions provides diminishing returns. The findings suggest that architectural constraints on vocabulary resolution are more critical than raw parameter expansion. By balancing data and vocabulary density, researchers can optimize the model's internal representation of physical space. This reveals that structural limits can sometimes enhance a model's ability to learn continuous patterns. There are two primary interventions for healing the model's fragmented spatial map and improving its physical reasoning. The first intervention involves a dramatic reduction in vocabulary size from 7,000 down to just 128 tokens. This constraint forces the model to represent spatial data more efficiently, yielding a significantly improved R-squared value of approximately 0.99. However, the researchers identify a second and more robust solution called the ultimate fix. This involves abandoning discrete tokenization entirely in favor of formulating prediction as continuous regression. By treating spatial coordinates as continuous variables, the model can naturally maintain high-fidelity relationships between points. This shift removes the artificial boundaries created by discrete bins and allows for the precision required in mechanical calculations. Continuous regression provides the necessary structural foundation for a truly mechanistic world model to emerge. It represents a fundamental move away from language-based architectures toward those designed for continuous physical reality. While continuous regression inputs naturally preserve spatial continuity, they introduce a significant challenge known as the autoregressive decay. This phenomenon occurs when a model uses its own previous predictions as inputs for future steps. In a continuous regression framework, unbounded variables can suffer from catastrophic error accumulation during the inference process. Even tiny initial inaccuracies grow exponentially as the model steps through time. This failure is visualized by a red glowing spiral line showing a simulated planet losing its orbit. Instead of maintaining a stable path, the accumulated error causes the planet to crash into the sun. This highlights a critical trap. Spatial smoothness alone does not guarantee a functional or stable world model. Without a mechanism to correct these drifting errors, the physical simulation inevitably collapses. To overcome this, the architecture must find a way to achieve spatial stability alongside continuity. To address the problem of autoregressive decay, the researchers implement a technique called noisy context learning. This method involves injecting Gaussian noise with a sigma value of 0.1 into the historical inputs during training. By intentionally introducing small perturbations, the architecture is forced to learn robust error correction. Before this intervention, the model simulations resulted in planetary crashes as error accumulated. After applying noisy context learning, the model successfully maintains stable blue elliptical orbits over long durations. The noise serves as a training signal that teaches the model how to return to the correct path after a deviation. This process ensures that the transformer does not merely memorize a trajectory, but understands the necessity of orbital stability. By building this robustness, the model can overcome the inherent drift of continuous variables. This intervention is the second key pillar in the blueprint for physical discovery. Quantitative analysis reveals that continuous regression consistently outperforms classification-based tokenization in reducing mean distance error. When testing models across training sizes ranging from 10 to the power of 3 to 10 to the power of 7 tokens, regression remains superior. The experimental data shows a green line for regression with an optimal sigma of 0.1 staying significantly lower than the blue classification line. As the training data volume increases, the mean distance error for the regression model drops by several orders of magnitude. This evidence proves that regression is universally more effective for physical tasks requiring high precision. While classification struggles with the arbitrary boundaries between discrete bins, regression thrives by treating space as a unified field. These findings validate the architectural shift toward continuous inputs for physical discovery. They demonstrate that how a model processes its input is as critical as the amount of data it receives. Continuous regression provides the high-fidelity resolution necessary for any mechanistic world model. Even with a stable and smooth spatial map, standard transformer architectures face a challenge due to their long context windows. Typically, these models analyze an entire history of over 1,000 tokens to make a prediction. However, the reality of physics is defined by the principle of temporal locality. Newtonian mechanics is expressed as a second-order differential equation where the future state depends only on the immediate past. By looking at a long history, a model may find statistical patterns or global geometric shapes rather than the underlying local forces. To discover true physical laws, the architecture must be constrained to a much narrower temporal focus. Restricting the context length forces the model to find the mechanistic link between consecutive moments. This shift aligns the AI's processing with the causal structure of the physical world. It represents the final pillar needed to transition the model from a curve fitter into a physicist. The research identifies a distinct architectural phase transition that occurs as the model's context length is adjusted. Context length effectively acts as a dial that determines the fundamental nature of the learned world model. A line graph plotting R-squared scores against context length shows two intersecting regimes. At a context length of 100, the model enters the Keplerian regime, where its ability to fit global geometric shapes is maximized. Conversely, at a context length of 2, the model adopts a Newtonian regime focused on local forces. As context increases, the Keplerian score rises while the Newtonian score falls. This intersection on a log scale reveals a clear trade-off between global pattern recognition and local mechanistic discovery. If the context is too long, the model prioritizes memorizing historical distributions. If the context is restricted, the architecture has no choice but to learn the rules of motion. This transition defines the boundary between an AI that imitates paths and one that understands mechanics. In this regime, the model uses its entire history of past states to globally estimate the geometric shape of the orbit. It successfully discovers internal representations for specific geometric parameters, such as the semi-major axis and the semi-minor axis. Additionally, the model captures the Laplace-Runge lens vector with high precision. Bar charts show that the R-squared values for these parameters reach approximately 0.998, indicating a near-perfect reconstruction of the orbit's shape. However, this model is essentially a sophisticated memorizer of historical distributions. It views the planetary path as a static geometric entity to be traced rather than a dynamic system governed by force. While highly accurate for seen data, it remains bound to the specific trajectories it has observed. This Keplerian world model identifies what the orbit looks like, but does not understand why it moves that way. By restricting the context length to 2, the model is forced to adopt the identity of a Newtonian physicist. In this regime, the architecture must estimate the future based only on the 2 most recent states. This constraint forces the model to step forward mechanistically, calculating the instantaneous gravitational force. The internal representations discovered by the model reach an R-squared of approximately 0.999 for force magnitude and vectors. This means the model has independently identified the core physical law where force equals the product of masses divided by distance squared. Red bar charts confirm that parameters like total force and its directional components are represented with near-perfect accuracy. Unlike the curve fitter, this Newtonian world model understands the underlying cause of motion. It represents a transition from observing geometry to discovering the mechanistic forces that generate it. This approach allows the AI to generalize its understanding to entirely new physical environments. Comparing the Keplerian and Newtonian architectures reveals fundamentally different approaches to physical understanding. The Keplerian architecture is global and geometry-based, relying on long context windows to estimate orbital shapes. Its nature is characterized by memorizing historical distributions of trajectories seen during training. In contrast, the Newtonian architecture is local and force-based, operating under a strict context constraint of 2. This setup forces the model to discover causal invariants that apply regardless of the specific data distribution. While the Keplerian model is effective at predicting familiar patterns, it lacks a grasp of the fundamental forces that generate them. The Newtonian model moves beyond observation by identifying the mechanistic rules of motion. One architecture essentially serves as a sophisticated mapmaker, while the other acts as a rule finder. Understanding this distinction is vital for developing AI that can generalize its knowledge to entirely unseen physical scenarios. The research highlights a significant predictive paradox where longer context lengths yield higher accuracy despite a lack of physical understanding. A graph plotting mean distance error against future steps shows that larger context lengths, such as 100, achieve the lowest error rates. In contrast, the error is highest for a context length of 2. This occurs because global geometry is more robust to noise than the iterative integration of local forces. A model that understands the overall shape of an orbit can stay on track more easily over long horizons. However, this high predictive accuracy does not mean the model has discovered the underlying physics. It indicates that the model is a superior curve fitter rather than a physicist. This finding warns that low aerometrics can be a misleading indicator of true machine intelligence. Researchers must look beyond accuracy to determine if a model has truly captured causal physical invariance. Mechanistic models demonstrate their true value by breaking the distribution barrier that limits traditional curve fitters. A curve fitter is inherently bound to the familiar trajectories and data distributions it encountered during training. When faced with unknown realities, it often fails because it cannot find a matching historical pattern. In contrast, a mechanistic model successfully decouples physical rules from historical data. By capturing the invariant where force equals mass times acceleration, the model can generalize perfectly to entirely unseen scenarios. It does not need to have observed a specific trajectory if it understands the underlying forces that create it. This ability to operate beyond the training distribution is the hallmark of a functional world model. It allows the architecture to apply fundamental principles to solve problems in novel domains. By prioritizing causal discovery over data imitation, researchers can build AI systems that are more robust and adaptable. The blueprint for AI discovery combines three critical architectural components to force the emergence of a physical world model. First, the use of continuous coordinates ensures spatial smoothness, allowing the model to perceive the physical field with high fidelity. Second, injecting noisy context with a sigma of 0.1 provides the spatial stability needed to prevent orbital decay. Third, restricting the context length to 2 enforces temporal locality, which aligns the model's focus with the structure of Newtonian differential equations. These three interlocking constraints prevent the model from taking shortcuts like global curve fitting or simple data memorization. The result is a generic transformer that is architecturally pushed to learn a true mechanistic world model. This configuration demonstrates that specialized physics engines are not always required to discover the laws of nature. Instead, the right set of structural constraints can guide general-purpose architectures toward deep causal understanding. This provides a clear path for using neural networks as tools for genuine scientific breakthrough. The study from Stanford University concludes that true intelligence involves discovering mechanisms rather than just fitting curves to data. Architectural constraints are not a hindrance to this process. Instead, they serve as the essential catalyst for transforming a generic architecture into an AI scientist. By restricting context and ensuring spatial stability, researchers can force neural networks to uncover the fundamental laws of motion. This transition from Keplerian geometry to Newtonian mechanics marks a significant milestone in machine learning. However, the current boundary of this work lies in two-dimensional environments. A practical next focus involves scaling these inductive biases to more complex, multidimensional physical systems. This research proves that the path to deeper artificial intelligence lies in the careful balance of flexibility and constraint. It offers a new paradigm for how we design models capable of true scientific discovery.